An atom is the smallest particle of an element. It is made of three main particles: protons, neutrons, and electrons. Protons have a positive charge and are found in the nucleus. Neutrons have no charge and are also found in the nucleus. Electrons have a negative charge and move around the nucleus in energy levels. Most of the atom's mass is in the nucleus because protons and neutrons are much heavier than electrons. But most of the atom is actually empty space. Now, let's look at the notation. The atomic number, Z, tells us the number of protons. The mass number, A, tells us the total number of protons and neutrons. So, to find neutrons, we use neutrons equals mass number minus atomic number. For example, beryllium has mass number 9 and atomic number 4, so it has 9 minus 4, which is 5 neutrons. For ions, the number of electrons changes. A positive ion has lost electrons. A negative ion has gained electrons. The key idea is simple. The identity of an element is determined by its number of protons. Isotopes are atoms of the same element with the same number of protons but different numbers of neutrons. Because they have the same number of protons, they have the same atomic number. That means they are the same element. But because they have different numbers of neutrons, they have different mass numbers. Remember, protons have a positive charge, neutrons have no charge, and electrons have a negative charge. For isotopes, the key particles are protons and neutrons. Let's look at carbon. Carbon-12 has 6 protons and 6 neutrons. Carbon-14 also has 6 protons, but it has 8 neutrons. So both are carbon because both have 6 protons. But they are different isotopes because they have different numbers of neutrons. Carbon-12 has a mass number of 12. Carbon-14 has a mass number of 14. In isotope notation, the top number is the mass number, A. The bottom number is the atomic number, Z. So carbon-12 is written with 12 at the top and 6 at the bottom. Carbon-14 is written with 14 at the top and 6 at the bottom. The bottom number stays the same because both atoms have 6 protons. The top number changes because the number of neutrons is different. Isotopes usually have similar chemical properties because chemical reactions mostly depend on electrons. But they can have different physical properties because their masses are different. For example, heavier isotopes can have higher density. They can also diffuse more slowly than lighter isotopes. Some isotopes are stable, like carbon-12, while others are radioactive, like carbon-14. Hydrogen also has isotopes. Protium has 1 proton and 0 neutrons. Deuterium has 1 proton and 1 neutron. Tritium has 1 proton and 2 neutrons. They are all hydrogen because they all have 1 proton. But they are different isotopes because they have different numbers of neutrons. The key idea is this. Isotopes are different forms of the same element. They have the same number of protons but different numbers of neutrons. Relative atomic mass is the weighted average mass of the naturally occurring isotopes of an element. Atoms of the same element can exist as different isotopes. These isotopes have the same number of protons but different numbers of neutrons, so their masses can be different. Relative atomic mass is compared with carbon-12. Carbon-12 is used as the reference standard and its mass is assigned as exactly 12. For example, naturally occurring chlorine has 2 main isotopes, chlorine-35 and chlorine-37. Chlorine-35 makes up about 75% of natural chlorine. Chlorine-37 makes up about 25%. So we do not use a simple average. We use a weighted average. The calculation is 75 times 35 plus 25 times 37 divided by 100. This gives 35.5. So the relative atomic mass of chlorine is 35.5, not a whole number. Now look at lead. The mass spectrum shows 4 isotopes of lead: lead-204, lead-206, lead-207, and lead-208. Each peak shows the relative abundance of that isotope. Lead-204 has an abundance of 2%. Lead-206 has 24%. Lead-207 has 22%. And lead-208 has 52%. Because lead-208 has the highest peak, it is the most abundant isotope. To calculate the relative atomic mass of lead, multiply each isotope mass by its percentage abundance, then divide by 100. So the calculation is 2 times 204 plus 24 times 206 plus 22 times 208 divided by 100. This gives 208 divided by 100. This gives 207.2. The key idea is simple. Relative atomic mass is a weighted average based on isotopic abundance, so it is often not a whole number. A flame test is used to identify metal ions. When a sample containing metal ions is heated in a flame, the electrons gain energy. These electrons jump from a lower energy level to a higher energy level. But this excited state is unstable, so the electrons fall back down to a lower energy level. When they fall, they release energy as light. The color of this light is characteristic of the metal ion, so it can be used to identify the ion. Now let's look at the mass spectrometer. This part is HL, or higher level. First, the sample is vaporized. This turns the sample into gas particles. Second, the atoms are ionized by electron bombardment. Electrons are knocked off the atoms, forming positive ions. Third, the positive ions are accelerated by an electric field. Fourth, the ions pass through a magnetic field and are deflected. The amount of deflection depends on the mass-to-charge ratio, written as meters over. Ions with a smaller mass-to-charge ratio are deflected more. Ions with a larger mass-to-charge ratio are deflected less. Finally, the detector records the ions and produces a mass spectrum. This spectrum shows the relative abundance of each isotope. Now let's look at Rutherford's gold foil experiment. Alpha particles, which are helium nuclei, were fired at a thin sheet of gold foil. Most alpha particles passed straight through. Some were deflected at small angles. Very few were deflected at large angles. And a tiny number bounced straight back. From this, Rutherford concluded that most of the atom is empty space. He also concluded that the positive charge and most of the mass are concentrated in a very small, dense nucleus. The electrons occupy the space around the nucleus.